In basic game theory, we often model decisions as happening simultaneously. Everyone reveals their move at exactly the same time. But markets rarely operate that way. They unfold over time. One firm acts, another reacts, completely changing the math of rational behavior. To see why, look at a standard simultaneous model. This is the classic normal form, or a bimatrix. Each cell represents a potential outcome, where players choose their strategies in a vacuum, completely blind to their opponent's actual move. We find a Nash equilibrium here by identifying mutual best responses. But this static grid ignores chronological reality. It evaluates a Tuesday move as if chosen at the exact same moment as a Friday response. Sequentially, the game tree shows the incumbent threatening a price war to deter entry. But if the entrant calls the bluff, the incumbent maximizes profit by accommodating them for 2 instead of fighting for 1. The threat is mathematically hollow. That standard is subgame perfect equilibrium. It requires a player's strategy to be mathematically optimal overall, but in every isolated sub-branch of the game, even those we never expect to reach. To find it, we use a mechanical process called backward induction. Instead of projecting forward from the start, we go to the absolute end of the timeline and solve in reverse. Solving this tree requires backward induction. At the terminal nodes, player 3 chooses H and player 1 chooses Y. Stepping back, player 2 optimizes with C and F. Anticipating these guaranteed reactions, player 1 chooses B to secure their highest payoff. Backward induction turns a messy sequence into a clean set of nested equations, proving any strategy relying on an irrational future reaction will completely collapse. Once we understand how sequential logic prunes away empty threats, we can calculate the exact financial value of a credible commitment. Consider a 2-stage market model. In stage 1, firm 1 chooses a level of investment, labeled K. This represents upfront capital that modifies their own technological capability or lowers future production costs. In stage 2, both firms observe that specific investment and simultaneously choose their market outputs, which we label A and B. By the logic of backward induction, we have to solve stage 2 before we can determine the optimal investment for stage 1. In the second stage, both players maximize their profit by setting the partial derivative of their utility with respect to their own output equal to 0. Solving these equations yield reaction functions, mathematical rules that dictate exactly how much product one firm will manufacture based on the output of the other. Notice that the investment K only appears in firm 1's formula. But because firm 2's optimal output depends directly on what firm 1 produces, that initial investment mathematically ripples across both equations. A stage 1 investment exerts its true power by rewiring the opponent's entire reaction function in stage 2. Knowing exactly how the second stage will play out, firm 1 returns to stage 1 to choose K in order to maximize their total payoff. To find the absolute maximum, we take the total derivative of firm 1's utility with respect to investment K. This tracks the complete chain of impact. The first term is the direct effect. This represents the immediate financial improvement from the investment itself, independent of any competition. The second and third terms are indirect effects. They capture how K ultimately shifts the equilibrium output levels for both A and B. But we apply the envelope theorem here. Because firm 1 already behaves optimally in stage 2, the partial derivative of their utility with respect to their own output, A, is 0. That entire middle term drops out of the equation. We are left with a highly focused expression containing the 2 true drivers of investment value. The remaining product is the strategic effect. It isolates the exact profit gained by manipulating the opponent's optimal behavior. If this strategic effect is positive, a rational firm will deliberately overinvest in capacity. They pay a premium today, specifically to force a competitor to retreat tomorrow. We can translate this abstract calculus into a geometric model of quantity competition to see exactly how the manipulation functions. Let's map the strategy space. Firm 1's output is tracked on the horizontal axis, and Firm 2's output is on the vertical axis. These downward sloping lines are the reaction functions. Because an increase in production by one firm causes the other to pull back, we refer to these products as strategic substitutes. Before any investment occurs, the market settles at this intersection, dictating Firm 2's initial production level, B star. Now Firm 1 makes their cost-reducing investment, K.
Because production is cheaper, they are willing to output a higher quantity. Their reaction function shifts outward. Look at the new intersection. Firm 2 is mathematically forced to produce less. The strategic effect is positive. Reducing the opponent's quantity increases the market price, directly boosting Firm 1's profit, entirely separate from their initial cost savings. Strategic interactions are not static. They are dynamic processes that can be shaped by upfront commitments. Subgame perfection provides the mathematical lens to predict how those commitments will be perceived, separating genuine leverage from empty posturing. The calculus of commitment measures the exact ripple effect that action generates across an interactive system. For an industrial strategist, the internal benefit of an investment is secondary. The true value lies in the reaction it extracts from a competitor. Rationality requires looking down the game tree, calculating the derivatives of reaction, and engineering a future that rivals have no choice but to accept.